In order to maximize the speed of a computer, or reduce the power consumption of the computer, we want to minimize the size of our circuits. In this lecture, I will provide a definition of minimal Boolean expressions and present a useful set, but by no means exhaustive set, of Boolean identities that can help you minimize the size of your circuits. When we translate a truth table into a Boolean expression, we normally begin by finding every row that has an output of 1. We can translate these rows into expressions by using a complemented variable when we see zeros and non-complemented variables when we see ones, and adding those literals together. Because these variables are ANDed together, we call it a product term. We can find the product term for this 3rd row, 5th row, and 8th row with the same procedure. Finally, we OR the product terms together. As a quick aside, a literal is a variable that is either complemented or not complemented in a product term. So this expression has 3 variables, 4 product terms, and 6 literals. If a product term contains all 3 variables like these, it is called a minterm. We number minterms for convenience, and so the number of the minterm corresponds to the binary number of the row that generated the product minterm. So this is minterm 1, minterm 2, minterm 4, and minterm 7. A minimal form of a Boolean expression is one which first minimizes the number of product terms, and then, among expressions with the minimum number of product terms, it has the fewest literals. Let's consider this truth table. There are 2 ways to create a Boolean expression from this truth table. The first method is to OR the minterms together, just like we did. This method would yield a fairly large, complex circuit. If you are observant, though, you might have realized that this is the truth table for the OR operation. Not surprisingly, this expression yields a much simpler circuit and is the minimal circuit for this truth table. The first expression has 3 product terms and 4 literals, but the second expression has only 2 product terms and 2 literals. So the obvious question is, how do we prove that these 2 circuits are equivalent? One tool among many tools that we can use to simplify expressions is the Boolean identities. Here I present 4 of the basic identities. Each of these identities appears in 2 forms, one based on the OR operation and one based on the AND operation. These truth tables here can be used to prove these identities. If you want to spend some more time looking at these and memorizing these identities, they're all available at the end of the video, so feel free to fast forward to see a single table with all of the identities. The next property is called the distributive identity. Again, the distributive identity has an OR and AND focused versions. Form 1 should be fairly intuitive, as it is analogous to the distributive property in algebra. Notice how the Form 1 distributes both the literal and the AND operation across the OR operation. Form 2 does the same thing and distributes both the literal and the OR operation across the AND operation. Alright, let's put these identities to work. Up here we have our non-minimal solution, and down here we have our minimal solution. And over here I have the Boolean identities that I just finished describing. So when I look at this expression here, the first thing I notice is that this product term and this product term differ by 1 literal. As well as what I notice is that this product term and this product term also differ by 1 literal. So I'm going to want to have 2 copies of this one. So I can use the idempotence here, which tells me that I can reproduce this and it's still going to be the same expression. So I have x prime or y. I'm going to produce a duplicate here of x, y, and then I'll just keep the rest of this the same, x or y and y prime, or x and y. The next, I want to use distribution because now that I have these common literals, I'm going to do two distributive properties, and I'm going to have x prime or x ANDed with y. I'm pulling out the and and the y, or I'm going to pull out this x here, so I'm going to have x, y prime, or y. Now, since I have this x prime or x, that's going to be my complementarity property, and I can see that x or x prime is equal to 1, so I have 1 ANDed with y, or x ANDed with 1. Finally, I can use this identity property where I have x and y. 1 is equal to x, so this is just going to be equal to y or x. So now I can see that I have f is equal to x or y. Just to be able to recap, and you can see what I did step by step, here is everything in its gory detail. So you've just finished learning how to translate a truth table into a Boolean expression, and then how to minimize that Boolean expression with the Boolean identities. Remember, a minimal form of a Boolean expression is one that implements the expression with the fewest number of product terms, and then the fewest number of literals. Minimizing a Boolean expression is a skill that takes a good deal of practice. So I recommend doing as many practice problems as you can for this topic so that you can become adept at remembering the Boolean identities and then knowing when to use them.